Section 5.1, Trigonometric Identities. Here we have our fundamental identities, our reciprocal identities. Here we have cotangent of theta equals 1 over tangent of theta. That would also tell me that the tangent of theta equals 1 over cotangent of theta. Secant of theta equals 1 over cosine theta. Therefore, cosine theta would equal 1 over secant of theta. And cosecant of theta equals 1 over sine theta. That would tell me that sine theta equals 1 over cosecant theta. We also have our quotient identities. Tangent of theta equals sine theta over cosine theta. In our unit circle, we knew that sine theta would equal y, and cosine theta equals x, or in other words, opposite over adjacent. We also could have the reciprocal of that, which is the cotangent of theta, equals cosine theta over sine theta. Identities continued, we have the Pythagorean identity. Again, in the unit circle, we know that on our unit circle we have sine represented by our y, which would be squared, plus cosine theta is represented by x, which is squared, equals 1. Therefore, in a unit circle, x squared plus y squared equals 1. And that's how we achieve sine squared theta plus cosine squared theta. There, we can create from this identity the next two Pythagorean identities by taking sine squared theta plus cosine squared theta equal to 1, and divide both sides by cosine squared theta. Sine squared theta over cosine squared theta would give us tangent squared theta plus cosine squared theta over cosine squared theta, which is 1, equals 1 over cosine squared theta, which would give us secant squared theta. If we would like to find 1 plus cotangent squared theta equals cosecant squared theta, all I would do is divide each side by sine squared theta, and that would achieve this Pythagorean identity. Dividing by cosine squared theta on both sides gave us this Pythagorean identity. Also, we need to consider other forms of the identities. For example, we have the Pythagorean identity, but there are times I might need to solve this for sine squared theta. And that would give us 1 minus cosine squared theta. Or if I might need to solve this for cosine squared theta, and that would give us cosine squared theta equals 1 minus sine squared theta. Whichever one needs to solve the problem, I can change these or make alternative forms of these to make a viable option in my problem. Next, let's consider negative angle identities. In the diagram, I have a positive theta and a negative theta on our unit circle that generate points on our circle. I can identify sine theta. Sine theta is going to be opposite over hypotenuse, which is y over r. And negative theta, I can have sine negative theta equal to, again, opposite over hypotenuse, but that would be a negative y over r. So we can see that sine theta and sine negative theta are opposites. Therefore, to get these to be equal, I need to make sine theta negative. And that's how we generate sine negative theta equals negative sine theta. For cosine, what I need to do is to identify those in our unit circle. So I would have cosine theta equal to, on our positive theta, I would have a negative x as my adjacent and r. So that would be a negative x over r. Cosine negative theta equals, again, adjacent over hypotenuse, which would again be a negative x over r. So we can see that cosine theta and cosine negative theta are going to be equal. And that's why we generate this negative angle identity. For our tangent, we can have tangent negative theta equal to, and I know that it is sine negative theta over cosine negative theta, which is a previous identity. Now I can simplify that further. Tangent negative theta is equal to, well, I know that sine negative theta is negative sine theta. And I know that cosine negative theta is just cosine theta. Therefore, tan negative theta is equal to, and I know this identity to be tangent of theta. And then I just bring down the negative. Therefore, tangent negative theta is equal to negative tan theta. And this holds true for the reciprocal functions. On previous slides, we've identified identities. And we've actually used identities to prove other identities. So we've already started examples of using identities for solving problems. Here's a continuation of an example. What we have is tangent theta equal to a negative 5/3, and theta is in quadrant 2. That'll become important if we need to find sine or cosine or one of their reciprocal functions. And what we want to do is find the value of every function that's given to us. We want to find secant theta knowing that I have tangent theta equal to a negative 5/3. So what we want to do is look for an identity that relates tangent and secant together. From a previous slide, I have the Pythagorean identities. And we can see that one of those Pythagorean identities do relate tangent and secant. So what I want to do is substitute the value of tangent into that and find the value of secant. So I'm given tangent squared theta plus 1 equals secant squared theta. Now, all I do is substitute the value that's given to me. That is, tangent of theta equals a negative 5/3. So, negative 5/3 is substituted into tangent, but that is squared, plus 1 equals secant squared theta. This gives me 25/9 plus 1 equals secant squared theta. Let's find the sum of these. Common denominator is 9. That's going to give me 34/9 equals secant squared theta. Now I need to take the square root of both sides. And that's going to give me secant of theta equal to the square root of 34/3. Now recall, they gave us some more information to determine the value of secant. And that information that is I am in quadrant 2. And I know that secant is a reciprocal of cosine. And in quadrant 2, cosine is negative. Therefore, secant theta equals a negative square root of 34/3. Continuing with the example, they want me to find the sine of theta given tangent theta equals a negative 5/3 in quadrant 2. I've brought over the Pythagorean identities to see if we can get a relationship between tangent and sine. As you can see, none of these Pythagorean identities do give that relationship. So what I need to do is find another identity. And it just so happens the quotient identity gives us the tangent of theta equals sine theta over cosine theta. Now I can solve this identity for sine theta. So I multiply both sides by cosine theta. That gives me cosine theta times tangent of theta equals the sine of theta. And I know that the reciprocal of cosine theta is 1 over secant of theta times the tangent of theta equals the sine of theta. And I want to do that because on the previous part of this example, I already solved for the secant of theta, so I can use that solution in this part of the problem. Now all I need to do is substitute. That gives me 1 over, and recall from the previous slide, I know that secant is a negative square root of 34 over 3 times, and I substitute the given, which is a negative 5/3 for tangent of theta, and that equals the sine of theta. Continuing, I know the sine of theta, when I simplify, is equal to, now I find the reciprocal, which gives me a negative 3 over the square root of 34, times a negative 5/3. And the 3's are going to cancel. Negative times a negative is going to give me a positive 5 over the square root of 34. Now I'm going to rationalize to get the radical out of the denominator. I'm going to multiply by the square root of 34 over the square root of 34. And that's going to give me a solution of 5 square roots of 34 over 34. I do want to check the sign just to verify. I know that I'm in quadrant 2, and sine is positive in quadrant 2. Therefore, this is correct. 5 square roots of 34 over 34. Let's complete this example. Here they want me to find cotangent negative theta. What I need to do is to find identities that relate cotangent and tangent. Let's start with our negative angle identity. I know that cotangent negative theta is equal to a negative cotangent theta. And by the reciprocal identity, I know that cotangent theta is equal to 1 over tangent of theta. So I just bring over my negative, and now I have 1 over tangent of theta. Now I substitute the value of tangent of theta, bring down my negative, 1 over a negative 5/3. Find the reciprocal. That gives me a negative, and a negative is a positive, and that gives me 3/5. Therefore, cotangent negative theta is 3/5 when tangent of theta is a negative 5/3. In this example, I want to express one function in terms of another. Here, express cotangent x in terms of sine x. In other words, I want to write cotangent x with just sine values. I need to find an identity that relates these two. The closest one I have is our Pythagorean identity, 1 plus cotangent squared theta equals cosecant squared theta. But that doesn't get us to sine x. But if I use that in conjunction with our reciprocal function, cosecant theta equals 1 over sine theta. If I use both of those, I can achieve that. So let's write 1 plus cotangent squared theta equals cosecant squared theta. Then I can rewrite this using my reciprocal function. 1 plus cotangent squared theta equals 1 over sine squared theta. Now I want to isolate my cotangent squared theta by subtracting 1. Cotangent squared theta equals 1 over sine squared theta minus 1. Let's simplify the right side. That gives me cotangent squared theta equals, common denominator is sine squared theta. So sine squared theta over sine squared theta gives me 1 minus sine squared theta over sine squared theta. Now I can take the square root of both sides. That's going to give me cotangent theta equals the square root of 1 minus sine squared theta all over sine theta. Now I have cotangent theta written in the terms of just sine. In this example, I want to rewrite cotangent theta plus tangent theta in the terms of sine theta and cosine theta. Again, I need to relate an identity with cotangent and tangent to sine and cosine. To do that, I can use the quotient identities. For cotangent theta, I know the quotient identity is cosine theta over sine theta, plus tangent theta can be written with the quotient identity as sine theta over cosine theta. Now I need to simplify this expression by finding like terms. Here, my like terms are going to be sine theta and cosine theta. So I need to multiply the numerator by sine theta, cosine theta on each term. Here, sine theta, cosine theta times the first term. The sine thetas will cancel out, giving me cosine squared theta. And when I multiply the second term, the cosine thetas will cancel out. That will give me sine squared theta. And that will give me a common denominator of sine theta, cosine theta. Now I check to see if there are anything I can do to simplify this. And then I realize that cosine squared theta plus sine squared theta is our Pythagorean theorem. Cosine squared theta plus sine squared theta is actually equal to 1 by our Pythagorean identity. Therefore, 1 over sine theta cosine theta is our simplified solution. Our next example, find the remaining 5 trig functions of theta. We're given the sine of theta equals 3/4. We know that theta is in quadrant 2. And what we want to do is use the identities to solve this problem. We know that cosecant theta is equal to 1 over sine theta. It's a reciprocal identity. Therefore, we know that that is 1 over 3/4, which gives us 4/3 for cosecant theta. So we have sine theta equal to 3/4, and we have cosecant theta equal to 4/3. Now, what we want to do is determine another one of our trig functions. And since we know that sine and cosine are related, we can use the Pythagorean identity, sine squared theta plus cosine squared theta equal to 1. Substituting, I know that this is 3/4 squared, which is 9/16, plus cosine squared theta equal to 1. Cosine squared theta is equal to 1 minus 9/16. And when I simplify that, that's going to be 7/16. Take the square root of both sides. That gives me cosine theta equal to the square root of 7/16. And when I simplify, that's going to give me the square root of 7 over 4. But I also know that secant theta is equal to 1 over cosine theta, which is equal to 1 over the square root of 7 over 4. Therefore, secant theta is equal to 4 over the square root of 7. Now what I need to do is rationalize, which gives me 4 square roots of 7 all over 7. Now that gives us cosine of theta is going to equal the square root of 7 over 4. And secant of theta equals 4 square roots of 7 over 4. But in quadrant 2, cosine and secant are both negative. Now, I need to find tangent or cotangent. And probably the easiest one to find is to find cotangent, because I know cosecant is already 4/3. So I have 1 plus cotangent squared theta equals cosecant squared theta. Now I can substitute 1 plus cotangent squared theta equals, I know cosecant is 4/3. Cosecant squared is 16/9. Solve. I subtract 1 on both sides. Cotangent squared theta equals 16/9 minus 1, or 16/9 minus 9/9, which is going to give me 7/9. When I take the square root of both sides, I get cotangent theta equal to the square root of 7/9, or the square root of 7/3. Now I know that tangent theta is equal to 1 over cotangent theta, which gives me tangent theta equal to 1 over the square root of 7/3. That gives me 3 over the square root of 7. And when I rationalize, that's 3 square roots of 7 all over 7. Therefore, tangent theta is equal to 3 square roots of 7 over 7, and cotangent in quadrant 2 and tangent in quadrant 2 are both negative. And here's what I started with, and here are my 5 other trig ratios using identities. Let's take a look at our last example. What I'm going to do here is just walk through the problem. The previous problem I actually worked out all the way through. Here I'm just going to walk through it. But the first thing we need to do is to determine the quadrant we're in. On the previous example, they gave us the quadrant. Here I have to determine it. Cotangent and also its reciprocal, tangent, are positive in quadrants 1 and 3. And sine is greater than 0. Therefore, sine is positive. Sine is positive in quadrant 1 and 2. This tells me that I'm going to be in quadrant 1. I need to have both cotangent and sine positive. Therefore, I'm in quadrant 1. And understand there are multiple ways to solve this problem. I just chose one in particular. So the way I started was I'm going to use 1 plus cotangent squared theta equals cosecant squared theta. In other words, the Pythagorean identity. I substitute in, and when I do, I solve for cosecant, and I get the square root of 13/3. I also know that tangent theta equals 1 over cotangent theta. That's our reciprocal identity. And when I simplify that, I get tangent equal to 3/2. So I have a given cotangent theta is 2/3. Tangent theta is 3/2. I determined cosecant theta to be the square root of 13/3. And also, I use the reciprocal identity for cosecant. Sine theta equals 1 over cosecant theta. And when I simplified that, I have sine theta equal to 3 square roots of 13/13. Then I went back to my Pythagorean identity and related tangent and secant. And when I substitute in, I get secant equal to the square root of 13/2. And I know that cosine theta equals 1 over secant theta. And when I simplify that, cosine theta equals 2 square roots of 13/13. And this wanted me to find the other 5 trig ratios, given cotangent theta is equal to 2/3 and sine theta is greater than 0. And here I have the given and the other 5 ratios that I determined.